Hello, so today we're going to talk about topic 9, recursive functions. And this is a topic that's going to be very interesting to relate to what we've seen so far with Turing machines and what we're going to see later with lambda calculus. In many ways, this topic kind of is a good transition between these two topics and a good introduction to lambda calculus in some ways. Um, so recursive functions are going to bring the question of language and in some sense, yes, computability. Here our language is going to be arithmetic, but we're going to have the same kind of question: what can we express? What can we compute with recursive functions? This is a very powerful topic and very important topic because it leads to very important results. And one of them is that with recursivity, you can very quickly get a Turing complete language, programming language, for instance. So if you take the example of Prolog, you look at Prolog as a language. It doesn't look like very expressive. You just have facts and rules. But because the rules can be recursive, it makes this language very powerful and actually Turing complete. So this is a very, for computation purposes, even though this piece looks more mathematical, for computation purposes, it's a very important topic. Okay, so what's the basic idea of recursive functions? The basic idea is building up from a very minimum ground objects and very minimum amount of ground functions. So our basic starting point really for recursive functions is the only really objects constant we need is 0. And we're going to build up everything from that, all arithmetics. And so that's really going to be the principle and kind of the leitmotif of recursive functions is this the idea of building up. So you probably remember doing proof in high school using recursion, proof by recursion. How do you do that? Well, you prove first that it is true for a certain index k equals 0 or k equals 1, depending on, and then you show that so it's true for k equals 0, and if it's true for k equals 0, you show that for all k, it is true also for k plus 1, right? If it's true for k, it will be true also for k plus 1. So more strictly speaking, you should say true at k implies true at k plus 1. Okay, so you need these two conditions, which we call usually the base case and the inductive case, to show that it is true for any k, any natural number, any index. And really this kind of base case and inductive case is really the ground for a recursive function. We're going to start with the base case 0, and we're going to build up from that for 0 plus 1, 0 plus 1 plus 1, etc. So we're going to show that it's true for any k plus 1, and this is going to build a function, say addition. This is how you're going to start. Actually, the very basic one is not going to be addition. It's just going to be the notion of successor, right? Successor of 0 and a successor of 0, etc. And from this notion of successor, you can build up the notion of addition, right? So the way it is going to work is that we're going to take this basic function we just described, whether it's succession or addition, and we can build up on top of that and say, well, let's take this function and build up on top of this function to create a higher level function, right? So if this is successor, this can be addition. If this is addition, this can be multiplication. If this is multiplication, this can be exponential. So you really build up operations and mathematical concepts on more elementary concepts. That's the idea. We're going to see more concretely how it works, but I just want to give you the big picture. And so it's not just building up on zero, right? The first one builds up on zero, but then we build up not on objects, but on functions themselves. And that's the whole idea of recursion. So we have several pieces for to define primitive recursive functions. The first, trying to adjust a little bit here. The first important piece is that we need initial functions. And the initial functions can be two. There is the constant function 0 and the successor function. So you first have the constant 0. As I say, that's the starting point. You have the successor function. S, right? So S of 0, really, if you translate it in natural number, S of 0 is really 1, right? And S of 0 is 2, etc. And then the second initial function that we need is called the projection function or the identity function. So it's going to be, and you have different notations depending on the reference, but it's going to be P I n of x1 xn, so that's the number of arguments, equals xi. So it's really a projection, just to say take the ith element in the vector or in the n tuple here, in the tuple here. Okay, so these are the initial functions. They are a starting point for recursive functions. These initial functions are recursive functions, okay? They are recursive functions, but there are special recursive functions that we're going to use to do this building up. We can use any of these initial recursive functions. So they are like axioms. We define them as recursive functions, and they are our ground function that we can use to build up more complex function. But to build up the more complex function, we need two other recursive, properly speaking, recursive scheme and functions. We need composition. So composition is allowed. You can have for h of x and uppercase x like that, usually define a tuple of small x's. Can be defined as a composition of f and g1 of x, gn of x. So you can compose f and g. And G can be distributed among all among a series of arguments. Okay, so that's composition. You are always allowed to do that, right? So I can, already from what I have here, I can see that, for example, I'm going to try to build an example. If I call it, h of x equals P1 n, right, of G1 of x, That is, h of x is therefore recursive function, a valid recursive function, because I'm following this rule. I can compose it, and because it's projection, and actually G1 is not defined here, so let's make it a little bit more precise. I can say, well, it is, S of x, and they are all, well, you can say S1 of x, Sn of x, right? So they are all different successors with different different combination of succession, right? Sn of x is really s of s of s of s n times of x, right? So that is a recursive function because I build it only from what I have here so far. So it's perfectly fine, and I can say that h of x, therefore it's a projection on the first one, so it's going to be s1 of x, which is s of x, right? Which is basically x plus 1, right? In regular arithmetic, it's going to be x plus 1. So that's a recursive function because I'm using only what I'm given here. Okay. So far, you can do things with that, but you won't go very, very far. What is really powerful is the primitive recursive scheme, or for short, we're going to call it primitive recursion, that we add on top of that. And you have here now the two cases, right? The base case and the inductive case. I'm just making sure that it's still recording. Yes, it is. Okay. The base case is going to be hx0 equals f of x, and hx s of n equals g of x n h x n. You will encounter different notations. This one is borrowed from the Fernandez book, but it amounts to the same thing, right? Okay, so that's a base case, that's the inductive case. The case for 0, the case, the other cases, the case for it is still true for n plus 1, right? That's the recursion here. So that's really where the recursion occurs, right? Now, the recursion, properly speaking, is here. Now, we need this, right? Without the base case, you cannot build anything, right? Without the zero case, the whole thing falls apart, right? You need to ground in at least one object, which is 0, our starting point here. Okay, so with all of this, that is enough. You can build any recursive function is going to be defined recursively by those, right? So of course, once you define a recursive function, you can use that recursive function to define a higher level recursive function. The only condition I didn't precise here, the auxiliary functions here, f and g, that I use here, have to be recursive functions, right? They have to be primitive recursive. Primitive recursive functions. And right now, in this first part, we focus on primitive recursive functions, and we'll define later what primitive means and why we say primitive, right? There is a larger set of functions, general recursive functions that contains other functions that we're not going to see that here. I will see them in the part 2, okay? So right now, just assume this is primitive recursive functions, the definition of primitive recursive functions. Okay. So let's see maybe a little example. For instance, the addition. If I use that, how can I define the addition, right? Well, I can define addition by saying, well, I'm going to need these two things, right? I do not need, this is what I'm going to use to define, right? This plus this, but ultimately when I define a new primitive function, recursive function, I just need these two, and then I'm going to use the fact that f and g must be primitive recursive. I can use, if needed, the notion of successor, which is already actually included here, right? And the notion of composition, which is actually also used here in some sense. So, but I can also reuse that. By the way, just to note, right? Why is this recursive? Because here G, right? H is defined in function of g, which is itself containing h, right? So you have here the recursion here, right? H depends upon g, which depends upon h, right? So here is the recursion. Here is the self-reference, right? Okay, so if I define addition, I'm going to start with the base case, right? Plus x0. And well, given my definition here, it's going to be equal to a certain f of x, right? And I'm going to have to define plus x Sn equals g x n h x n. Here, so note that here I only copied that, right? I only copied the definition. I didn't say yet anything in terms of semantics of addition. I didn't define yet addition. I just copied that. I'm just saying I'm going to use the definition. Now I'm going to need to define f and g, say exactly what they are to give meaning to the addition. Note that I'm using the lowercase x because here I do not need a vector. I just need one number, right? Addition just naturally applies to just natural numbers. So, okay. So now I need to define f and j for this to make sense and to be completely defined, right? This is not enough to just say that. What is f and j? Well, what do I mean when I say x plus 0? I apply the addition to x and 0, I'm going to get x, right? So f of x, you can say, well, it's just equals to x. If you want to be more precise and really use what we have here, we can say f of x equals pi 1, 1 of x. I'm just going to do a projection here on the first element, which is the only element, which is x, right? So here I'm really purely using what I'm being given, right? If I kind of miss this step, I would be a little bit ambiguous and imprecise because I would not be strictly using a function, right? When we said f has to be a primitive recursive function, it has to be somewhere here, right? Now, that's for f, and for g. So what is g of x n h of x n? Well, that looks kind of this one looks complicated. I mean, you can see why is okay. The successor of n is going to have to be defined in terms of n. That's the induction principle. How do you define the plus 1 based on the k plus 1 based on k? But why do we have all of these other things, right? We could just have j of h x n. Well, it is not always used, and here we're not going to use it. But sometimes we need it. Sometimes we need x and n. We need these elements, and so it's just for us to have them available. And it is correct to refer to x n or h of x n to build up the recursive function. Okay, and we'll see a case where we actually need x. So how is it going to be defined? Well, very simply, we're going to say g, okay, we're going to say g equals a composition of S and P3. P33. So that means so it's the round here. Circle round means composition. So I'm just composing S of P33. That's my G, right? I replace G by that. That's how I define it, which is okay because I'm using the successor function and I'm using the composition, which I'm allowed to do. And I apply that, therefore, to all of this. H, right? Remember, H is actually my function that I'm defining here. So I've been forgetting to replace that. sorry about that. H is my definition function, right? H is here, here, and here in my definition. So I need to make sure that it appears here, here, and here. So I'm applying this G to the 3 arguments. And of course, because here of the projection, I'm going to forget about these 2 first arguments. So it's going to be S of only the 3rd argument, which is plus xn. So, so basically we have the case that x plus the successor of n equals the successor of x plus n, which really makes sense, right? So here we have the recursion. So in the end, we have plus x. So how do you define the addition with respect to the successor of a number? Well, it is a successor of the addition to the number, right? If I try to say that in English, it's how you compose the concepts. Okay, I know it's a lot just to define addition, but here we have defined addition completely recursively using only this definition. Now I can use that definition of addition that has been established to define something more complicated, like multiplication, for instance. So let me get a piece of paper and try to define now multiplication. So if we try to define, so really, it's like we started from 0, we define addition, and then we're going to start from addition, we're going to try to define multiplication. We always need a 0 though, right? The 0 is still grounding us, as you're going to see. So let's define multiplication. Let's call it star, for instance, right? Star x 0 equals g of x, and we just we just copy this definition of recursion. Equals, sorry about that, it's, here we call it f, I have to use the same notation, and here we call it g. G of x n star xn, right? So how are we going to define f? Well, f of x equals 0. And I do not need more than that here. 0 is a constant. It is 0 is in itself a recursive function by definition. And now, what is g? Well, I'm going to define g. I'm going to say that g is defined by addition. Right. So basically, how I'm going to define the multiplication by n plus 1 is the multiplication by n plus, it's x times n plus x. So it's the addition. It's adding the thing to what has been multiplied so far. Adding one more time. That's basically the concept behind that. I'm going to express add one more time, and that's how I'm going to define multiplication. Inductively. So g is going to be defined by plus that is going to be composed with 2 arguments, which I can do, right? I can do composition, multiple arguments composition. That's part of my definition. One is going to be p13 of my arguments here. Right? As long as I reuse exactly the composition. If this is uppercase x, I have to reuse x in all the arguments here, right? And then p33. So I'm using 2 pieces in the projection, 2 pieces in the argument through projection, xn star xn. Oh, sorry about that. I realized that it was out of the camera, probably. I'm going to check again if you can see. Yes. Okay. Sorry about that. So I hope you can see that now. So I'm defining G as, right, that's my G, right? Composition plus of plus and 2 projections. So basically, what am I saying here? I'm saying, well, G basically is the addition of the first piece, which is X. So I'm you know, when I do projection, I'm just deleting all of these and just keeping the first one. Addition of X and the multiplication xn. So that's what it is. The multiplying x by the successor of n is the same thing as adding x to the multiplication of x by n, right? So what am I saying in plain, sorry, here I should look, what I'm saying in plain math, right? When I say that right, okay, so when I say that, right, when I say that rewrite the important piece equals, and that's my definition, and again, it's a completely legal definition in the sense that I am using, yes, I am using something new, plus, right, that we have not defined here, but it is okay because plus has been defined already as a recursive function. So I can build up on that, upon that, right? So plus has been defined, so now I can use it, right? But my only conditions here, f and g, are primitive recursive functions. So I'm composing plus because the composition of primitive recursive functions is a primitive recursive function. So I'm fine. I'm still in the correct definition. Now, just in terms of meaning, what are we saying here? Well, really, in plain math, we're saying x times n plus 1, right? Successor of n is n plus 1, equals x plus x times n, right? Well, there is nothing problematic here, right? If you do x times n plus 1, if you develop that, right, you get indeed x times n plus x times 1, right? So x times n plus x, right? So, you know, in other words, x plus x times n. Okay, which is exactly what we express here. So we saw 2 examples, addition and multiplication, how addition build up from really the very primitive definitions, functions that are given in the definition, and how we can build up on that to build also multiplication.